All right. So line integrals, part 1, section 15.2. So last couple of lessons, last couple of classes, we talked about what a vector field is. And then we talked about a couple of different ways that we can find derivatives of vector fields. We talked about the curl and we talked about the divergence, which are different ways of finding derivatives. So what we want to do now is start talking about the idea of a line integral and what that has to do with a vector field. So today we're not going to talk about vector fields with line integrals. We're going to talk about scalar fields and line integrals, just so we can introduce the topics. So when we're talking about a line integral, it's very similar to a regular integral in single variable calculus, except instead of integrating along the x-axis, we're integrating over some arbitrary path in the plane. And we want to evaluate that integral along a curve instead of along an interval on the x-axis. So it would actually be a little more accurate to call them curve integrals, because our path is usually not a line. It can be a line, but it's usually not. So what we're doing in 2 dimensions is we want to sum some function of x and y along a path. And we're going to call our path or our curve C. So for example, if we had a wire that was bent in the shape of a curve, and we knew the density, the mass per unit length of the wire, and we wanted to find the mass of the wire. So that f of xy would be our mass per unit length, some function of x and y, and the wire's in some curve shape, and we want to add up all the little pieces of mass to get the mass of the entire wire. So our method, our technique, is what we're going to do for this first part is we're going to write our curve C as parametric equations. So we want to parameterize our curve. So we're going to say that x is some function of our parameter t, and y is some function of our parameter t. And if we extended this to 3 dimensions, we would just add a z component. Everything else stays the same. And we're on some interval on our curve a less than or equal to b. Sorry, a is less than or equal to t, less than or equal to b. And we're assuming that our curve is smooth. C is smooth. And when we say our curve is smooth, we say that what we're saying is our derivatives, x dx dt and dy dt, are continuous, and they're not 0 at the same time. So we don't have any cusps or anything like that. So that's how we're starting. So let's draw a little picture of what we're talking about so we can come up with our method of evaluating these line integrals. So here's our xy plane, and we have a curve in the xy plane. So my curve I'll draw in red. So here's my curve. So this is my curve C. And we're going to talk about several points on this curve. We'll say this is point 0, point 1, point 2, etc. And then up here we're going to look at, just in some segment of the curve, we're going to look at some very small piece. And somewhere in that little piece of the curve, we're going to have our coordinates x sub I and y sub I. And we're going out here to p sub n, points of n. And p sub 0 corresponds to t equals a, and p sub n corresponds to t equals b. So we're traveling along this curve from t equals a to t equals b. What we're going to do is divide the curve into small little pieces, and each little piece is going to have a length delta s sub I. So we're finding the length of these little pieces, we're dividing it up into little lengths, and what we want to do is form the sum, and by now this should be hopefully a familiar argument. We want to sum I equals 1 to n as we go along this curve, f of x sub I, y sub I, delta s sub I. So we're multiplying the function value at this point x sub I, y sub I, times the little arc length measurement in that segment. We're going to take the limit now as delta s sub I approaches 0, just like we've done for a lot of other things, and we come up with our definition of our line integral. So as we take the limit as delta s sub I approaches 0, we get our definition. So our line integral of f along our curve, and this is how we're going to define our line integral, is this limit of this sum as delta s sub I approaches 0. And the way we note a line integral is we write our integral over c. So the little c says we're on some curve c. F of x, y ds is the limit as delta s sub I approaches 0 of this sum. And c, again, we're saying c is a smooth curve. So there's our definition of a line integral. And now we're at the same place we've been for our definitions of lots of different kinds of integrals. We need a way to evaluate this. So this is our definition, but we don't want to evaluate it by taking this limit every time. So we want to come up with a nice way to evaluate this. So everybody good with our definition so far? And we'll talk about how we evaluate these things. Okay. All right. So back in chapter 12, we said that ds, or we came up with ds, this arc length differential, we talked about this, is the magnitude of r prime of t dt. So we worked on this idea of finding the arc length of a vector valued function, and this was our arc length differential. And we said back then that this arc length differential was going to be important for lots of different things. Well, here's one of the things that we're going to use it for. And just as a reminder, the magnitude of r prime of t is the square root of dx dt squared plus dy dt squared. We can show that if f is continuous, that our line integral this line integral over our curve C of f of x, y ds equals the integral from a to b. Those are the endpoints of our interval on our curve of f of x of t, y of t, times this arc length differential. And usually you'll see it written just this. I wrote it this way just to remind us how we find the magnitude of r prime. This is the same as the integral from a to b of f, and I'm going to write x, y. We express our function in terms of our parameterization. That's what this x of t and y of t means, times the magnitude of r prime dt. And we're saying that x is some function of our parameter, y is a function of our parameter, and a is less than or equal to t, less than or equal to b. So this gives us a way to evaluate our line integral. We parameterize our curve in some way. We practiced in the past parameterizing curves when we talked about parametric equations, when we talked about vector value functions. Did a similar thing both times. We express f in terms of our parameters. We find the magnitude of r prime, and that becomes our integral. F expressed in terms of our parameters, magnitude of r prime dt. And that will give us a way to evaluate this integral. A couple of important notes. The way that we parameterize our curve introduces an orientation. So we're saying this direction is positive. When we parameterize our curve, we're saying this direction is positive. So we always get an orientation when we parameterize a curve. And we've talked about the orientation of the curve previously as well, which direction you travel as the parameter increases. So depending on how we parameterize, we could travel along the curve in different directions. That will make a difference. That wouldn't make a difference if we're finding the mass of a wire or something like that. But when we start talking about vector line integrals over vector fields, the parameterization can change the sign of our line integral. If f of x, y is 1, so we're just evaluating the integral from a to b of r prime dt, we just get the arc length of the curve. That was our definition of the arc length. We can also think of this line integral as an area. So if f is positive, so if it's we have some surface above the xy plane and we have a curve in the xy plane, what we're looking at is the area that's below the surface along the curve. So we can think of it as the area, the lateral area, the area of a fence that's built in the shape of the curve, and its height is given by f of xy. We can think of it as an area. Any other interpretation of what a line integral is depends on what f of xy is and what our curve is. So we can't say a line integral is this thing until we define what f is and what our curve is. But those gives you some idea of how we can think of a line integral. All of our arguments are valid if we add a z component. So if our curve is in 3 dimensions and our function is a function of x, y, and z, we just add the z component. And we can also make our curve, rather than a smooth curve, we can make our curve a piecewise smooth curve. So we can say C can be piecewise smooth, and piecewise smooth again means a union of a finite number of smooth curves. So we're joining smooth curves together. So instead of one nice curve, we could have a situation, just to draw a little picture here, and then we'll start evaluating some of these line integrals. Our curve could be something like this, and then this, and then this, and then this. So this would be, and we're traveling along this way. So that would be a piecewise smooth curve. And what we would do to evaluate our line integral is call this curve 1, call that curve 2, that curve 3, and that curve 4. And we would just form a sum of the line integrals over each segment of those, each piece of that piecewise smooth curve. And we worked with this idea a little bit in the past as well. All right, so there's our method of evaluation, a couple of ideas about line integrals and piecewise smooth curves. So what we want to do next is I want to talk really quickly about a couple of reminders about parameterizing curves. It's been a while since we've parameterized curves. And then we'll evaluate some of these line integrals. So let's say we want for all of these, for each of these examples, we want a piecewise smooth parameterization of this curve. And hopefully this first one should be easy. X squared over 16 plus y squared over 9 equals 1. So we want to parameterize that curve. So how do we, first off, what is this curve? An ellipse. Major axis is vertical or horizontal? Horizontal major axis. So we want to parameterize this ellipse. Do we remember how to parameterize an ellipse? The x squared and the y squared and this equals 1 should always suggest sines and cosines. So what I'm going to say to parameterize this curve is x equals 4 cosine t, y equals 3 sine t. Need an ellipse, not a circle. So x squared over 16 plus y squared over 9 would give me cosine squared t plus sine squared t, and I get 1. And we would say 0 less than or equal to t less than or equal to 2 pi to go around the ellipse once. And so my parameterization RT for the curve is 4 cosine ti plus 3 sine tj. So that's one way we could parameterize a curve. And would we travel around the ellipse clockwise or counterclockwise? When t is 0, x is 4, y is 0. So we start on the x-axis there. When t is pi over 2, x is 0, y is 3, so we're moving from the x-axis up to the y-axis as t increases. So our orientation would be counterclockwise.
Anti-clockwise?
All right, this next one, let's look at this one. We're going to have a picture to go from, and we want a piecewise smooth parameterization. So we want a piecewise smooth parameterization of that curve. So what do we need to do here? We're going to parameterize each piece. So I would call this C1, C2, and C3. And it doesn't matter how we parameterize each piece. We don't have to make the time parameter match at each endpoint. We just need to travel along this curve for each parameterization, and then we'd form our sum. So for C1, what would be a good parameterization for curve 1? X equals t, that sounds good to me. And y equals t squared. And our interval would be 0 less than or equal to t, less than or equal to 2. So that would parameterize our first curve. So we could say our t for our first curve is ti plus t squared j. How about for curve 2? Well, let's do the easy one first. What's the easy component for this one? Y equals 4. Everywhere on that curve. And we want to parameterize x, so we go from 2 to 0. So how could we do that? X equals negative t. And we want to let t go from negative 2 to 0. Negative 2 less than or equal to t less than or equal to 0. So that would be a parameterization of that curve. You could parameterize it. The way I thought of it was to parameterize and say x equals 2 minus t and let t go from 0 to 2. But this one, yeah. When we evaluate our line integral, our parameterization doesn't really matter. We say the line integral is independent of the parameterization. And then finally C3. So let's do the easy one here. What's the easy one on C3?
Y is always 0.
Y is 0?
I mean X.
X is 0?
It's Monday morning.
X equals 0? X, Y. What's the difference? What's 90 degrees among friends, right? And then we want to let y go from 4 to 0. So y equals 4 minus t. And we would say that 0 less than or equal to t less than or equal to 4. So that would be a parameterization of the third curve. And so if we were evaluating our line integral, we would sum the line integral over these three different curves. We form 3 different line integrals and make our sum. So when I always like to point out in chapter 15 when we're starting, we bring things together. So we're bringing these vector valued functions back together, this idea of parameterization, and we're putting that together with this idea of integrating a multivariable function. So kind of throwing those things all together, mixing them up. All right, questions so far?
The graph you drew.
That was just the path that was given for that particular problem. This one versus no, this is an ellipse.
Okay, I thought we were.
No, this is 2 examples. Sorry.
Okay.
So this is example 1,
Okay.
and this is example 2. Separate problem. You thought we were redefining an ellipse to look like this?
Yeah. I didn't know it was very hard.
Right. All right, so let's evaluate a line integral now. We want to evaluate this integral for xy ds, where our curve They give us our curve. They're nice. We don't have to parameterize anything. All right, so this problem, they already give us our curve, and our curve is parameterized. So we don't have to parameterize this curve. So what we need to do is we need to find the magnitude of r prime. We express our integrand, our f of xy, 4xy, in terms of our parameters, and evaluate our integral. So we find r prime. R prime is going to be I minus j, and the magnitude of r prime is square root of 2. We express our function f of xy in terms of our parameters. So the integral, line integral 4xy ds is going to be the integral from 0 to 2. 4 times t times 2 minus t times the square root of 2 dt. So let's simplify this a little bit. I get 4 square root of 2 integral from 0 to 2 of 2t minus t squared and this is a nice easy integral to evaluate. So we get 4 square root 2 times t squared minus t cubed over 3, and we're evaluating that from 0 to 2, and that comes out to be 16 square root 2 over 3. So, for example, if this were our density function, and we had a wire in the shape of this curve, what is this curve, by the way? We don't have to know precisely. It's a line. This is a line. So if we had our wire in the shape of the line, and our density function was given by 4xy, that would be the mass of that wire from 0 to 2. If 4xy were a height above the xy plane, then this quantity, 16 square root 2 over 3, would be the area of one side of the fence that was above the line and below the surface. Okay, are we good with that example? All right, next one. So we want to evaluate this line integral x squared plus y squared ds along our curve. And our curve is counterclockwise around x squared plus y squared equals 4 from 2, 0 to 0, 2. All right, so our curve is x squared plus y squared equals 4. So we're along this circle. So here we are on the circle, radius 2. And we're going counterclockwise along that circle. And we're going from 2, 0 up here to 0, 2. So for this one, we do need to parameterize this curve. So how are we going to parameterize this circle? That x equal cosine, and we need to account for the radius.
Over 2.
Times 2. So we want, when we get our sine squared and cosine squared, we want to factor out the radius, so we get x squared plus y squared equals 4. So x is going to be 2 cosine t, y equals 2 sine t, and our parameter t varies from what to go from 2, 0 to 0, 2. 0 less than or equal to t less than or equal to pi over 2. 0 to pi over 2 is going to take me a quarter of the way around the circle. All right, so now we're almost ready. We need to find r prime. So we're saying that our vector value function is 2 cosine t I plus 2 sine t j. The magnitude of r prime is going to be what here? Magnitude is going to be 2. So I get 2 cosine t quantity squared plus 2 sine t quantity squared. So I get 4 times sine squared t cosine squared t, take the square root. So r prime is going to be 2. Magnitude of r prime. Magnitude of r prime is 2. And then we express our integrands in terms of our parameterization. So we get the integral, our line integral of x squared plus y squared ds equals the integral from 0 to pi over 2. X squared plus y squared is 4. That's what on the curve x squared plus y squared equals 4. Magnitude of r prime is 2. And dt.
Oh, my goodness.
So we get 8 integral from 0 to pi over 2 dt. So we just get 4 pi. Too good to be true. So this looked like it could be possibly not very nice with this x squared and y squared, but because of our curve, everything turned out very nicely. All right, we good with that example?
So now we can find the magnitude of the bus, the wheels on the bus going round and round. Or the intensity of the singing.
The intensity of the singing?
Yes.
All right, let's look at one last example.
Because the intensity of
All right, so we're going to evaluate. We're going to evaluate the line integral x plus 4 square root y ds along our curve, which is the line from 0, 0 to 3, 9. So first thing we need to do is parameterize this line from 0, 0 to 3, 9. So how are we going to parameterize this line? Let's say r of t equals, what is it? Ti hat plus 3t j hat. So y equals 3. This line is y equals 3x. So that would be our parameterization for that line. And we're saying 0 less than or equal to t less than or equal to 3. Everybody good with how we came up with the parameterization? Yep. Okay. And then we find r prime. Calculating these line integrals becomes very mechanical. Let's find r prime first, and then we'll do the magnitude. R prime is I plus 3j. So the magnitude of r prime is going to be the square root of 10. And then we're going to write our write our function, x plus 4 square root of y ds is going to be the integral from 0 to 3. And we want to write our function in terms of our parameter, so we get t plus 4 square root of 3t is our function, times the magnitude of our prime, square root of 10, dt. So not a difficult integral to evaluate. This one turns out nicely. And when we evaluate this integral, we just end up with a t squared over 2 and a t to the 3/2 for this integral. And we get 57 square root of 10 over 2. All right. Questions on that one? Line integrals, scalar fields, not particularly difficult, concept, not particularly difficult procedure. So the important things: parameterize your curve, express your function in terms of your parameter, and we have to include this quantity magnitude of our prime in our integrand. All right. There we go.